Doskonale.
Good evening. Today our speaker is Marzena Sniegowska. She's related with our observatory from 2013. 13, and in 2016 she defended a bachelor thesis working with Łukasz on Gaia transients. Then in 2016 she defended a master thesis working with Szymon Kozłowski on AGN, and then she escaped and go to the TSAMK, where she complete PhD with Bożena working on the Changing-Look AGN, and today she will talk something about Changing-Look,
yeah.
but observation.
Yes.
Okay. Bożena, floor is yours.
Okay, thank you. So hello everyone, thank you for coming in such a pretty day. Yeah, so now I'm working at Tel Aviv University in a group of Benny Trachenbrot, and yeah, I will mention first about the Changing-Look. What are those? How to them, and what are the problems in it? And then I will mention also some like other nuclear transients phenomena which are possible in AGN. And also problems with modeling them, of course, because we always have some troubles. I will start from the drawing, which probably you've seen many times, but it's quite important. So when we are talking about the classification of AGN,
Excuse me, stop. The screen is not shared.
Okay. What is the sharing button?
is it okay now?
Yeah, much better. Thank you.
Oh, yeah. Okay, good. Yeah, so in the center we have supermassive black hole, which is surrounded by accretion disk. Then a bit farther we have broad line region, in which broad lines are created. And then a bit farther we have narrow line region. We may have jet. We don't. Not always. Mostly we don't actually. And I will not be talking about jetted sources. And then we have also obscuring torus farther. And the classification of AGN mostly depends on broad lines. If we see them, as you can see here in optical spectrum, we see H beta line, and this is the same line. Yeah, it's also H beta, but here it's much narrower. It's comparable to this O3, which is also visible here. Yeah, but here we have nice broad emission line. And for some sources, it was we noticed that they changed the spectrum, so that they changed from this to this or vice versa. And this model is telling us that if we have, for example, observer here, and we are looking here, the torus is obscuring the broad line region, so we don't see the broad lines which are created there. So we see just narrow lines. But if we change if we observe the source again and we see that it changed, of course, it's not like we change the position or the source cannot change the angle, yes, the inclination. It has to be some other process going on. That's me, and it's not working. Okay, I will just help. In a while, I will show you examples of sources in which we saw these transitions. What I have to do? Just
try again.
Okay, great. So here we have yeah, quite old paper, and you can see here 3 optical spectra. This first one is from 1974, and here we see H beta, and then like the year after it disappeared, then it's, yeah, something maybe it came back. And here is another source, another example that we have H beta, which appeared and then, yeah, disappeared. And for some sources, we also saw that this H beta line appeared and then disappeared. And here you can see only this narrow component, which is created in narrow line region, which is much farther than broad line region. So we assume that this is constant. It will not change. And I was telling you now about spectra. Now I will come to photometry. Because the Changing-Look are associated with changes in the light curve and in the spectrum. We need both conditions. And I'm talking now just about optical one. And here you can see the best observed actually AGN with many data points even here. And you can see that they are not constant. And they have some non-stochastic activity going on. We say that this is semi-periodic. We cannot use periodic. And we were wondering what phenomenon could cause them. And in general, why to study those sources? Because many of them are detected recently, but not because they were not present before, just because we didn't have this telescope power as we have now. So now we are detecting not just those few sources I shown you, but we have few hundred by now. And we still don't know exactly the reason. There are a few reasons possible for now. They are a challenge to the UNIFI model. We can also check then the properties of the host galaxy, for example, of the sources. And to check some insights into AGN physics, like some ionization parameters, density, we can check what is changing there actually. And the first systematic search of those sources, because as I mentioned previously, we just had a few. And the first one where we saw more than few, it was by Chelsea MacLeod. And what they did, they chosen a sample of observed archival spectra. They were following the photometry, and if the source changed, they were using it with pan-stars survey. If the source changed significantly the luminosity, then they did follow-up spectrum. And here you can see one example of source like this. The first one is like SDSS is the earliest spectrum, and you can see something which is very common for the brightening Changing-Look, which is this UV slope here. And here you can see this H beta really nicely. Also here there's some helium. And another spectrum taken as a follow-up is this one from Bosch, which is this black one. Yeah, and we don't have this UV flare anymore. And also the broad H beta disappeared. We still have some H alpha here. Another discovery of Changing-Look, it was done just using archival data. So what they did in this work, they took two publicly available surveys, SDSS and LAMOS, and they compared the spectra for the same sources. If one source was classified as galaxy, and then as a galaxy, it means that the spectrum was just showing this normal galactic activity. And for another survey, it was showing AGN, which means also those emission lines. And then still you have to do a quality check by eye, of course. And they found more than 20. So for now, we have less than 50 known sources. It was, 2018. And here I'm just telling you about spectroscopy, because we don't do this photometric. At least by then there was not so many photometric data points to measure exactly the timescale, how the source behaved, to see what was going on with it. There were few more systematic searches of it, especially recently. You can see that this field is growing with some other surveys like Catalina real-time survey. Another one was also from DTF. And how they do it is always the same, that you are checking if you have archival spectrum, mostly from FDSS or from some older facilities. And if you see the significant change in the light curve, then you are doing follow-up spectrum and you check if it was significant change. And for now, what do we know about them? That they are showing dramatic change in the brightness and the spectral appearance in X-ray, N/ or optical, and I will be talking just about the optical. They prefer low Eddington ratio, so they are not very high accreting sources. That was noticed for them. For now, we know, I think, around 400, roughly, and there is not much dependence in the black hole mass or the luminosity in them. They are rather homogeneous samples. And there are some possible scenarios, and I decided to classify them in two classes, extrinsic or intrinsic one. So in extrinsic, we have a variation of obscuration, and let's focus for a while on this. This is it's quite unlikely, but in all of them we have some problems, to be honest. But I will first mention the problem about this. When you try, for example, to check the polarization of the source, because extrinsic means that we have some variation of obscuration, so we should have some cloud which is passing our line of sight, yes? And then the luminosity drops. So this model would be for this changing look, which are dropping in the luminosity. First problem actually is with the size of this cloud. How big the cloud should be to cover such a huge region, yeah, in such a short time. Such a short time, I mean less than 10 years, which is rather fast for AGN. And there was one work in which they checked small, like 10 Changing-Look AGN. They did thing which is called spectral polarimetry. So you are checking the polarization of the medium around. And if you have a cloud, it should be rather polarized, yes? It should scatter something. But they got quite low level of polarization. And also if the cloud is passing through our line of sight, the polarization should change. It did not, because they did this check. Yeah, so those are the problems, the size and the polarization, which is not changing. But I said it's unlikely, but it doesn't mean it's impossible. There was one source found by Grisha Zelten, who is a PhD student at Tel Aviv University. And here on this light curve, you can see ZTF data, which is optical survey. And then it was followed also, those dots, those violet and yellow are from WISE, which is infrared, yeah? And you can see that this infrared, it's actually following this drop in luminosity, yeah? Because infrared is a bit farther, so it needs time to react to what is going on in optical. So there was this drop, which was only 2 miles, actually. And you can see that also the spectra reacted for it. There was a first spectrum is this from 2001, and then also H beta disappeared. So what was reported in this paper is that it seems it probably is some obscuration, but we don't have an answer how one cloud can hide it. Okay, let's move on to another possible scenarios. And now we will just focus on intrinsic one, because most of those scenarios are about intrinsic, because you have more playground here to change parameters. So in some cases, probably tidal disruption events can provide us the answer, but there is also the problem, for example, in spectrum. Tidal disruption event has really nicely defined spectrum that you should see some remnants from the star, yeah? which in most of Changing-Look, it's not visible. There is also a problem we have once we have some repeated events. In AGN, the standard tidal disruption event is unlikely to happen few times. I am not talking about partial one now. And also another problem is with the timescale, that the flares which we see in Changing-Look are longer than in typical tidal disruption events, because also tidal disruption events are known that they have all the same slope, which is minus 5/3. And on this, I will spend most of my talk, which is possibility of changes in accretion rate, which means that there are some changes in accretion around the black hole, and what kind of changes, whatever you like, it depends on the model, yeah? And then we have also some questions like what process would start some kind of instability in the accretion disk, yeah? Is it some radiation pressure, ionization, some magneto-rotational instability, whatever you like, yes? And will those instability give us the expected time scale? Because I'm talking about tens of years, but sometimes even months, yeah? And for most of them, you need some addition to lose angular momentum. So maybe some waves, maybe some winds, so probably something extra to add. Yes, and when we are talking about accretion disk theory, like the standard accretion disk, we are talking about 3 time scales mostly, like the dynamical scale, which is just to which means like propagation of the sound waves and the time which is needed to restore the hydrostatic equilibrium. The thermal time scale is to restore thermal equilibrium, and this depends only on the viscosity parameter alpha, which in models mostly is just the number. And another one is the viscous one, which also depends on the thickness of our disk. So we have 2 parameters to modify. Yeah, we can modify alpha, or we can modify this thickness of the disk. And in Keplerian disk, this one is the longest. And I did some simple calculations to show you more or less what those timescales are if we are just talking about theory. Yeah, we are taking some typical AGN with black hole mass, let's say 10 to 7. Yeah, this alpha is quite commonly taken when we are using some model. And first one is just light travel time. So for accretion disk, we have like 1 day. Broad light region is in 10, maybe 100 days. And then we have torus, and about cost is much farther, yes? If we are talking about dynamical time scales, yeah, for accretion disk, this is already in years. Yeah, a cost is too far to disturb it. And once we are talking about the viscous, which means some, yeah, physical change maybe in the thickness, yeah, then look at the years in accretion disk. That's not the time scale we thought, yeah? So maybe it's something about the thermal equilibrium, or maybe what we assumed about the source, because also here I assumed the geometry, very simple one, yeah? For accretion disk, I took this one, for BLR, this one. So maybe we should add something to this theory of standard accretion disk. And why I'm talking about the standard accretion disk, it's a very, for now, it's the best working theory, which is giving us the formula to compute things. We don't have to run the simulations, and it's quite nice to have some more or less working theory if you want to compare with observation, for example. Yes. And now I will tell you about the first model, which was done for one source, Markarian 1018. And I will show you here X-rays and optical, but that will be, I think, the only X-rays I will show you on this presentation. So the authors proposed here that this change, first let's look at the optical data. So here we have our archival spectrum from SDSS with really nice H-beta line. And then we have 2 other spectra taken like 15 and 20 years later. Yeah, and you can see that the change in the shape is quite visible, and also intensity, yeah, in comparison to this oxygen 3. Because in AGN, we are saying that oxygen 3 is always constant because it's so far, it will not change within our lifetime. So it's a really nice thing to compare. There is a problem if you don't have those lines, which also happens with some objects, but not in case of Changing-Look AGN. And this source was also followed by, I think, XMM observations, and it was modeled with the component, this one, which is called soft axis, and in which should be here. Yeah, so we have black hole, our accretion this, and in this model is assumed that we have it's called advection dominated accretion flow, which means that this is medium which is optically thin and also geometrically thick, and our accretion disk is geometrically thin but optically thick. In this, they didn't do any calculations. It's for now it's hand waving, yeah. But they assume that there is some kind of ionization instability, which is quite common, for example, in stars. Yeah, we see something really similar. And this ionization instability caused that this soft axis evaporated into ADAF because some physical parameters change. Maybe the density, maybe ionization, probably ionization parameter could change, yes? And then it caused this change in this visibility of the soft axis, and this X-ray reacted with, it's shown up in the optical. So, okay, very nice, it works for this Markarian 1018. The problem is that, for example, there is another source, which is also Changing-Look AGN. And the problem with this source is that we also saw changes in the optical spectrum, but there was no warm corona component there in the X-rays, which means that not for all sources this model will work, which I think suggests that for this class of objects, we may have few explanations, few theories. There is another, also, I think it's really nice example, and I will show you the spectrum. So first one is SDSS from 2000 with this really nice UV flare. And then after 10 years, you see this drop in UV, yeah? And here there is no H beta actually, but this drop is really, really strong. You can see in the flux, yes? And then after roughly 10 years, a bit more, but it came back to what it was with the shape. And the explanation for this source is that there was some triggering event, whatever, change in magnetic field, whatever change in the medium, and it caused the cooling front, which was going outwards, and then this matter was colder, so then we saw this, and it came back as a heating front, and caused us to see again the structure which we saw previously. So here we have another source, another explanation. It would be nice to have some theory which works for more than one source, yes. And here I want to show you the example why follow-up is important. And also like multi-wavelength observations, because then we can really see what's going on with the spectra. Here it was the start of the flare. Here are optical data, here is X-rays, and you can see that first we had optical flare, and then drop in the X-rays. Yes, and if we go from, this is the time when this started to rise, and you can see that H beta arrived. And it arrived after around 3 months from UV flare, which means that, yeah, because for the light, we have the speed, yes? We have the time, which means we can measure the distance, yes? And the distance is as we expected for BLR. So it was really nice confirmation that it's probably something happening around the black hole. And there are at least two papers. There was also really nice work by Claudio Ricci, and they did the follow-up observation in X-rays to monitor what really is going on. And as I told you previously, yes, we had UV and optical flare and then drop in the X-rays. And the theory, what could happen, it was called that there is some reestablishment of magnetic flux, that it's changed like in the sun, yes, we see that it could cause this drop in the X-rays and this flare which we saw in UV. There are also another ideas, for example, closed black hole supermassive binaries. And there was one work which showed how the luminosity would change, like how the shape would change if we have some tidal interaction between mini disks, but it was, yeah, without any modeling, it was just the idea which could be explored further. And now I will tell you about radiation pressure instabilities, on which I've been working on with Bożena. And mostly what we do, we are solving those two equations, which I decided not to put here. It's just a surface density of the accretion disk and the temperature, equatorial temperature in the accretion disk. And once we assume that they are equal to 0, we have this curve of solutions. And we are putting it into this plane, yes, with surface density and the accretion. And the one which have positive slope means that they are stable solutions. So we will just be focused on this radiation pressure one. And also this is called S-curve. And this S-curve you can plot for any radius in accretion disk. And also you can see that, yeah, it changes, yeah. Once we are going higher with the temperature, then advection dominates, yeah, closer to it. Once we are going closer to black hole, because then it's hotter then. Okay, and here it's an exemplary fragment of the light curve that we would see. And this mechanism is also seen, for example, in X-ray binaries. Yeah, it's like you just change the mass of the source in the equation, and you can, and also the temperature, and you can see how the light curve will look like. And we only focused on the timescales. Yeah, we are not touching spectra yet. It would be nice at some point to do, but not yet. And we have here 3 phases. So we are starting from here, which was, yeah, gas pressure, and we are slowly going up with the temperature, because we still have the equilibrium, thermal equilibrium, and the surface density is growing. Then the sigma is slowing down, but you can see that then the temperature grows, and it increases also with the luminosity, and then we have the cooling, and it's some kind of engine-like behavior in the theory. Yes, that's what we are assuming. And this I did for 10 solar masses, which is of course not for AGN, but I just wanted to show you, and it was easier to compute. Yeah, that's a case of X-ray binaries, and for some one particular radius in the accretion disk. And we will come back to this multiple changing look phenomena I was showing you, because we wanted to check if we will be able to get this timescale between the flares, roughly. Yeah, because with the shape, it can be hard, but let's see what we can do. So we constructed really toy model with Bożena, because we have black hole, we have our ADAF, which is this geometrically thick and optically thin medium. Then we have some unstable part of the disk. And we followed how this evolution of this zone will behave. If we compute those, this part, yes? Yes, and we did. For just different parameters, we were changing this parameter alpha, which is just the number in our model. We were changing also how narrow this part is, and how fast the source is accreting. And we were just comparing the timescale, yeah, because you can see that the shape, it's still quite questionable. And we managed to get those 10 years Yeah, and here I'm just showing you again the light curves of the previous, I would say, observed AGN. And also, Bożena decided to check one source, which was this one, GSM 069, and this is not Changing-Look, because there was another phenomena called quasi-periodic eruptions. They were just occurring in X-rays in sources 10 to 6 solar masses, so a bit lighter than AGN. But we wanted to see if we are able to get those peaks, which are very symmetrical, really nice. Not always symmetrical. Here it's not very symmetrical. For now, I think few more are known, but it's still quite less than 10, I would say. And we wanted to see if we are able to get the timescale, maybe shape, and then it would mean that those instabilities are causing it. Do I have the results? Probably not, because the timescales we got, the shape not really. And the differences between the QPE and Changing-Look AGN is, for example, that the broad emission lines are not appearing there, even if you have those. So this is just in X-rays. And also the duration, you can see it's like I was telling you about 10 years, and here we have hours. Yeah, so it's something different, but we thought, okay, in X-ray binaries it works. Maybe here also we can do something about it. And we were not the only one with the idea to do something about explaining those. There are already a few theories, like that we have some kind of warp disk, and then this tension between in this inner disk tearing, it's causing those flares. There are a few work which are showing quite complex white dwarf, which is called MRI. That we have some instabilities which are caused by some stellar binaries, or maybe more than binaries in some objects. And for now, the most like people are giving the most attention to those kind of models, which is this processing accretion disk with some in spiral system. And actually, it's if you check this light curve, you can see that okay, like we have some. Here it's more or less the same, the distance. Here not really, yeah. Here it's longer and then shorter. But also you can see that this is higher, lower, higher, lower. So it means that maybe it was actually something spiraling in the accretion disk. Yes, and just to not mess too much, I wanted to classify that I was telling now about QPEs, which are a bit different phenomena. That there is possible scenario for both of them, but this is the only thing which is tying those both phenomena. And for now, we still have small number of objects with good data coverage, because Changing-Look, we have few hundreds, but not with pretty light curves, so we cannot do that much for now. And we decided, okay, it does not work as we thought. So maybe let's add a bit more complex model. And for this, we are not computing just one part of unstable disk anymore. We were just computing the whole unstable disk assumed as accretion disk part with some extra corona. And we are staying with our ADA. And if you compute theoretically what would be the time scale for this 10 to 7 solar masses, we have thousands of years. So this is out of question. But if we cut our accretion disk, then we can get, okay, 85, which is not yet what we want. But if we cut more, maybe we will get what we want. So that's what we did. We were checking this model for a few cases. And in Changing-Look, we will be talking about 10 to 7. We used this time-dependent evolution. Then we added some boundary condition, extra flow from here, because we decided, okay, this will maybe shrink the time scale. Yeah, it didn't work as we thought. So then we were like, okay, let's add some other condition. Let's add magnetic field, because if you don't know what you do in astronomy, you can add a magnetic field, and you can explain many things by also adding in the modeling. So we decided with 2 models with some kind of extra accretion flow from disk to corona, And another model, it was that we were just blocking the flow between accretion disk and corona to speed up the process from the corona and from the accretion disk. Yes, and those are our results. This is the light curve. For now, we have more than almost 100 years, and you can see that it doesn't look as we thought. And here we will just focus on the amplitude, that it's quite high, but then it gives us also the playground that we can add a lot of things to shrink the time scale, because once we shrink the time scale, also the amplitude shrinks. Yeah? And we were still trying just to explain time scale, because with the shape of the light curve and shape of the spectra, we are not discussing it yet. We have to add more things to the model, or maybe not to do it in one, because this is just 1D model. And you can see that we have, again, those 3 cycle behavior, as I said, and exemplary light curves, because this didn't work. So we were like, okay, let's add magnetic field. What will change? And we have this gray line, which is accretion disk, and the red one is for the corona. And you can see that the higher magnetic field we are adding, then the corona behaves differently. And also we are going in some kind of different pulsation mode, I would call it. And if we cut the radius, we are getting some kind of subflares, which are not observable, but then we can play that, oh, maybe we are just seeing what is between those 2 flares, yes? And then I decided to play with this, how small this outer radius I can get to still see flares. And I got into 15 Schwarzschild radius. And I also wanted to check how it will affect the amplitude of the flares. And here it's in years, so you can see that still for QPE, it's we are not there with this model. Here I just wanted to show you how the period drops for different electron masses, and that's why we have model A and B, because we were checking 10, then 10 to 5, and then I was supposed to check 10 to 7, but I was getting nuns. So we were like, okay, let's do another model, because also what worried me, that here you see that it was dropping, with the higher magnetic coefficient, we were dropping with the period. This is in days still, yes? But in 10 to 5, at first I was getting the increase in period. So I got worried, okay, so what if for 10 to 7, I will just get this increase? And that's not what we wanted. But here I noticed, okay, for the higher magnetic coefficients, we are dropping with the period. For 10 to 7, we were not with this model. And this model A, it was this one, that we are adding extra accretion flow from accretion disk to the corona. Then we decided to check another model which was with so-called dead zone, that we don't have any flow between accretion disk and corona. And this I managed for 3 cases. And you can see that here I got, really worried, because the drop appeared for the very high, very, very high. It was 10 to 4 Gaussians, which is still physically possible. But for most of the time, the period was going higher. And here we just arrived to a different pulsation mode. So it was possible to get it. And I will show you this pulsation mode. Yes. So you can see here that this is like one group, another, and this is the last one. So this one was dominant group here, which is, it was quite worrying me that I am getting hundreds of years, and I was supposed to get 10. But here I managed at the end with some. But if you cut the outer radius, this is for 10 to 5 black hole mass, you can go, this is for amplitude. So then, you are around 0. But here, first we start with some ridiculous, yes, from minimum to maximum amplitude. But then with the period, yeah, because we were trying to shrink it to see if we are able to see this QPE, but I think with a very short outer radius, yes, around 15, it was something in hours, but then the shape was not really what we wanted. And then the question is, what would cause this outer radius? Yes, because you have accretion disk, and why something would be there as a cut? And we thought that first it could be caused by some maybe tidal forces, that we have some star which is giving us this gap, or maybe there is some smaller black hole which is orbiting around supermassive black hole 1 and is giving us this gap, so these waves cannot propagate farther. Yes, and now I will tell you about other AGN variability and some peculiar events. But yeah, I was mentioning for most of my talk about Changing-Look, briefly about tidal disruption events, but there are also some peculiar events in AGN, which are none of those two. And here you can see the light curve from the optical with this funny two bumps, yes? And then up you can see the data from WISE, which is infrared. Yeah, and you see that it's following the flare. Yeah, and from the light curve, you see that it's not. This is a typical tidal disruption event, light curve. So that's not this one. And for Changing-Look, we saw for those sources a change in the spectral lines. And I will tell you about it right now. Yes, the context. The context will be broad Bowen fluorescence lines in AGN, which were predicted many, many years ago by Hagai Netzer and Gary Ferland. And those are people who are working for almost the whole career on the photoionization codes. And they predicted, if you check this table, they predicted the flux, theoretical fluxes for the line, which should be visible in AGNs, in comparison to H beta. H beta, which is some commonly visible line in AGN. And if you know AGN well enough, you can see that there are some two lines, one of them almost as high as H beta, even higher, which are not visible in it. But the model from this 85 saw that it should be, yeah, because for this helium, we need extreme UV, and how those lines are created, that this helium gets de-excited, it excites oxygen, which is this one, oxygen gets de-excited and excites nitrogen. And it was present in the code of Gary Ferland, which is called Cloudy. But because they were not observable, why to waste CPU time for this? Yes, so they turn off those lines in the code, and now it's a problem because I wanted to compute how it will look, and I cannot because it's not in the code anymore. Yes, and the first source which was noticed with those lines, and people realized that this is actually this Bowen fluorescence. Was described by Bennett Trachenbrot, and you can see here that we have the light curve with UV flare, and mostly it increased in UV. In X-rays, not that much, like by 2, 3, but this UV got really extremely high, and archival UV, it was here when you wanted to plot it, and those are the new UV data. And I think here it will be the spectrum, yes, and here it's yeah, so let's focus on this right one. You can see here this oxygen doublet I was telling you. Then we have H beta, which we were also mentioning. And this is the black one is SDSS composite, because for this source there was no archival spectrum. But this blue one is the follow-up spectroscopy from this flare. And you can see that there was this thing visible with some double peaks, and you may say, okay, like this is where helium should be, yeah? Helium is so TDE because there is a dot line, but with double peaks and this nitrogen visible here, because you can see that those are two lines. It's not one line. Plus, here we have extra line, which was not here. Yeah, so it fits to what I was showing you from the theory. Yeah, so it was first robust identification of this nuclear transient. Yes, and for now we know around 10, I would say around 10, yes, and some of those are in progress. I will be telling mostly on Tel Aviv group, okay, because I am a bit biased since my affiliation is from there right now. And you can see here some examples of tidal disruption events like this one, yeah, that here we have some broad helium, almost like blurred with the thing which should be H beta. And here we have those another sources. And you can see that this shape is different. It's not because we have broad and then we have, yeah, broad, yes, with few tens of thousands. So it's not tidal disruption events because one, we have these extra lines, and another thing that the light curves do not match. And this is the latest published one, Bowen flare by Lydia Makriani with archival spectrum. So it's showing clearly that we didn't see this flare here, but after flaring event and this double peak, we see really nicely this spectral lines. And then what is telling us that it was an AGN, yes, previously, because we have those lines. Because we have AGN, it means we had this broad line region. We had broad line region, it means we had this dense ionized gas ready to be somehow excited from this UV flare. Right? And it would be really nice, for example, to check the properties of this gas before and after the flare. It would be nice if the code had this transition. Yes, and we go to my conclusions now, that many changing-look are being detected recently, and not only changing-look, also this really nice nuclear flares. We still, yeah, the more we see, the more question we have actually about them. But for now, what we should say that the follow-up is the key. Follow-up in the light curve, so in photometry, in spectroscopy, in general, in multi-wavelength. It would be so nice to have also polarimetry, because then it would tell us a lot about the gas there. The toy model which are presented, it was not only mine, all of them I presented are too simplistic. But we have to start from something, yes? And it will be nice to improve them, to introduce new parts to these models to see if we are able to recreate the spectra before and after the flare, and then we could get from it some physical conditions maybe, and some questions about this broad Bowen lines. Are there something somehow linked to TDE? Maybe it's some kind of TDE in AGN. Maybe it's some kind of recurring events. We don't know yet, and we will try to answer those questions at some point. Maybe. Okay. Thank
you. Any question?
I have a question about LSST and how the multicolor light curves will affect the different color.
So with LSST, it will show us, because we mostly need UV, because this UV, it will tell us, this near UV, I mean, it will tell us, because I am associating this UV flares with something which is near black hole, and also I'm not the only one. So then we have like this first, glimpse that, okay, this is not some obscuring, that's something inside the accretion disk. But still, I would say that without spectroscopy, we cannot say much. I mean, we will be able to say that something about the timescale, but without spectroscopy, it would be quite. I mean, it would be still better than what we have now, but it would be really nice to have follow-up spectroscopy as well.
And by spectroscopy, just to follow up this question, the more important for you is the wavelength range than resolution or signal to noise ratio. This is the main.
For me, I would say the most important is the ratio between fluxes of the line, because that would tell me the most, I think. And also the shape of the continuum as well. So the resolution is also important, but with low resolution, you can still do something if you see the line shape, because you see, okay, oh, this line appeared, so it's changed.
More question? Yes, Christian, please.
So the time series is a spectral model. You assume it's quasi-periodic variability, but it's stochastic luminosity. And then one calculate the power spectrum of luminosity.
I know where you're going, because if you have that few bumps, you can still say it's actually stochastic, right, Alex? Yeah, because Alex Markowitz is.
Minimum of 3 or 4 or 5 cycles is strongly preferred.
Yeah, so we should have more data for it to be sure this is non-stochastic. For now,
Thinking about total time series, if you calculate the power spectrum, it seems like the power, it would look like stochastic.
we didn't compute the power spectra of it. But I think it could be, maybe it was done by some, not by me. I didn't check it, but maybe it was done. Yes, probably it was done.
And if you see trends in the power law, then you are sure that it's not no matter the number of times. Because not looking at it's beta, but if I would look at the time series to the light,
I think for this NGC 5548 was done, because this source is, turned upside down almost with all research. So probably for this one, it was done.
And the other one that we showed look more like there was one event that changed look. So
no, I will argue that because it will. There were some small bumps, let's say, which we.
For example, when we start the scenario when there is a cloud, it looks like there was only one bar, right?
Yes.
So it would be completely different table than the one that we have.
I think so. Yes.
Okay, we have more question. The question from internet. So no see more question. Let's thank our speaker again.